pass you along with it?
So I don't have to worry about it.
Hello, everyone.
You're
Welcome.
So I'm for sure looking forward to it. Like, in the sense of just finally cashing
Like it's letting
in
people in.
all the suffering. I'm for sure looking forward to it. Like, in the sense of just finally cashing
It's letting people
in all
in.
the suffering. I'm for sure looking forward to it.
And then turn it like this.
Yeah.
All right, thank you.
Give me a second.
Oh yeah, go for it. Okay, I saw your picture rolling around on the screen.
Need another hand.
Yeah, this is gonna be.
I don't think. Can you turn it landscape? Oh wait. Dr. Bax. It's because we're engineers.
Horizontal's probably better.
Probably, but
I
this
think my
is what we
setup-
can manage.
I think I did not set it up to be horizontal, and apparently it needed to be set up in the.
Maybe if we set it back a little bit, we can actually see.
Hey man, yeah, how's it going? Going well, I guess. I was gonna text you and tell you I was getting some better over there if we were going.
It's gonna be a reflection of whatever is posted on the screen.
Do you have a wide camera?
Answer my question.
It's facing this way.
No, you should be good.
How the materials class is gonna finish.
So you walk.
Oh, it's way on the other side, it's like, okay, well, I mean, how many of these are there?
It's better. Much better idea.
So we're not gonna be able to see ourselves, but
It'll be all right.
that's okay.
He's already passed it. He's gonna do any more work in that class, and he's gonna pass.
All right, that's
I probably don't either.
So someone can actually read what we put up now.
You got the 90 on the test.
So you're good to about right there.
Half
Where you're at.
half of the screen is the ceiling and projector.
We can move it up close.
Well, we're not gonna be able to see if we do that.
Why are we not doing,
We can stand.
why are we not doing landscape?
Would you like to do it?
Well, no, I'll shut up.
Because that's gonna be inverted. The screen would, you wouldn't be able to read it.
Yeah.
We can go way higher.
Tuesday again?
Yeah, I had a,
Go behind me.
I think we can bring that.
We're going.
Is there a way to pause it?
This is the first
You know?
Yeah.
Stand up right here.
had a killer week last week.
At home tomorrow.
Well, we really just going into 219 and so it's
Y'all got more family down there? Or is your mom's family down there? Well, my mom's family.
almost had a 600 series.
I think that's good.
Like a 230.
All both sides. of my family down
2 weeks.
there.
There you go.
Oh, that's right, because 634.
Really?
Only 600 bid, I'll see you
Yeah,
tomorrow.
nice.
Are you ready? Are you ready? That's the most important question. Probably more ready than you.
Yeah,
I'm ready.
We're
messing
gonna
with pain.
I think I'll just tell them to stand close to the
Get
light.
them, get them.
It's a nice pen. Yeah, it is a nice pen.
Even
We only got one.
my first cousin on my dad's side.
We could have one person here and then another person about that out.
Yeah, that looks good. Mhm. There you go.
What, you couldn't be bothered to show up in the picture? Is that it, Colin?
I think Saturday morning.
Saturday morning, you're sleeping in.
Forgot about it.
Yeah.
Dude, it's always nice.
You guys got
Last year you did it right. I
Yeah.
remember last year you did it.
Yes, I think.
Well, because we had all these projects to do too.
We got the first two people in here, so when y'all switch,
I didn't get anything done this week.
talking, can you just kind
Because I'm
of
sick.
just swap? Like y'all can stand two and two, and then when it's your time to talk, just swap places so that you're closer to the screen.
This semester, I think too bad.
Would standing out be better for presenting?
Yeah, because then you're in the way of the,
The
slide.
way of the screen.
Yeah.
And then they'll just switch.
When you're doing introductions and stuff, you can stand right across it, right? But when you use the screen, you need to be there. Okay?
You know where the camera is? You understand this, right? You know where
A little bit.
yeah. Do we need to put tape down for you?
That works too.
It wouldn't hurt.
Yeah.
I can do that at the end, so I'll always in.
We'll make it do.
They had to be like located in the setting.
Of all the team, you should understand this better than anybody.
We had technical difficulties.
I do it once a semester, so.
I'll figure it out.
We're in
I didn't
vertical.
just try it.
Oh, we can't. No, the live stream set up for profile.
Yes.
Continue having fun. Look like you know, like you're professional, you know what you're doing. There you go.
You changed. There she is.
I'm coming.
This is just there for that presentation. If you wanna, if you do, you don't.
I'm sorry. I know, I'm not much, but I'm all I think about.
So, I have to provide after and he'll be the provider.
Ready?
All ready?
Yes.
There you go. Alright. Good afternoon and welcome to the final presentation for the seniors from the class of fall 2023. My name is Anthony Battistini and it was my privilege to lead these students through their senior design project. Buenos tardes y bienvenidos a la presentación final de los estudiantes de último año de Ingeniería Civil de la clase de otoño de 2023. Mi nombre es Antonio Battistini y fue un privilegio para mí guiar a estos estudiantes en su proyecto de diseño este semestre. We would like to thank our client, Habitat for Humanity, for entrusting us with the opportunity to improve your warehouse in order to help to do your important work for the years to come. And I would also like to thank the other faculty for allowing me to lead them in their design. So it's an honor to be the person who gets to see them through their final semester, see all the work that they can complete. So agradecemos a nuestro cliente Habitat for Humanity por encomendarnos la oportunidad de mejorar su almacén existente para ayudarlos a realizar su importante trabajo en el años de futuro. También me gustaría agradecer a los profesores por permitirme guiarlos en su diseño y por todo su ayuda en el proyecto. I would like to especially recognize Dr. Aldo Pignon, who worked alongside the team. You'll recognize him as well throughout the process, and he is going to be leading the senior design team next semester. Me gustaría reconocer especialmente Dr. Aldo Pignon, quien trabajó junto al equipo durante el semestre. Sin más demora, al equipo de estudiantes de Versa Engineering. Without further delay, the students from Versa Engineering.
Welcome, everybody. We're glad that you had a chance to meet us today and see our presentation over our project this semester. We had the Habitat for Humanity Improvement Project. I'm Gerald Elliott. This is Stephen Gubara with Colin Baggett, and we have James Amani here, and we are all Versa. All right. Joining us in this endeavor was Dr. Battistini, who is our senior design manager, and we also had Dr. Pignon, who helped as an assistant and started to learn the ropes of the class. All right. And so, as we proceed, we're going to work our way through the civil engineering sub-disciplines in this order, so we can solve all of the issues that were given to us through the scope of the project. So, here's our project. It's going to be on Chadbourne Street, right beside the Loop. It is a building. It's a warehouse that is split between Habitat for Humanity and Hartman Roofing. So our project mainly focused on the Habitat for Humanity, but we did venture into Hartman Roofing to help get an understanding of the building itself. For any locals, this is a layout just so you know a better picture of where it is. All right. Here's some pictures of the building and the interior components that we had to go and explore. So part of our project was to draw an as-built picture or diagram and CAD software so that we could give it to our client, Ms. Pam, so that she may further use it for any renovations or any further improvements later down the road. And so what we had to do is we go into here, take lots of pictures, take a tape measure, measure all of our structural components so that we could then draw out our components in our walls. So for our project scope, again, we had to do our CAD drawing where we had to model the structure as it is today, so it is an as-built drawing. And then we had to perform a structural analysis on the existing structure so that we could evaluate if it is safe for use in today's world or how they're using it right now. All right, so then we have to evaluate the existing watershed. One of the issues is that the building floods, lets water in through one of the walls, and we wanted to make sure we can mitigate that as much as possible so that we don't have any more damage to any materials they're selling or storing. We're going to determine a solution for the loading dock and parking. So one of the parking lots is a caliche-based parking lot, and it is unlevel, so we have a large pool of water that sits there when it rains, and it's inaccessible for anybody who is handicapped, so they can't roll across it very easily with a wheelchair. And then we have to find all the required permits and regulations that are going to be relevant for our project so that we can outline them for the client or any contractor so they may organize that accordingly. And then we'll perform a cost analysis of each different sub-step so that the client may take these as grants and submit them, because it's not going to be a lump sum. All right, and here I'm going to leave it off to Stephen Gubara, who's going to discuss the environmental division.
Thank you, Joe. The environmental scope overview for this project is that we need to run an impact analysis of the site, which includes the permits, the stormwater pollution prevention plan, identify best management practices, BMPs for short, and then possible future improvements to the site. The governing organizations on this project are COSA, City of San Angelo, TCEQ, TPDES, Federal EPA, Texas Pacifico Railroad, and then lastly, Texas Department of Transportation, TxDOT. Some permits required for this project are going to be a stormwater permit, which may or may not be a part of the project. As far as the EPA's Clean Water Act, that is something that we'll need a permit for, but this specific stormwater project permit is now required as it's over 1 acre and our site is smaller than 1 acre. The parking lot approach to the parking lot permit, a TCQ permit, and then lastly, an erosion control permit. The stormwater pollution prevention plan for this project, also known as the erosion control plan, describes the pollution prevention practices, potential pollution sources, and the BMPs on the project. Both are required by the EPA and TCEQ. In the bottom right here, I have a picture of the parking lot that we're proposing to add to the site, and surrounding it, I have a silt fence, and then the Habitat for Humanity. Some BMPs that will be used during the construction of this project are silt fencing, which acts as a temporary barrier device for sediment runoff, sound barriers, which help reduce the noise that are going to be happening during construction, such as air compressors, generators, and the chippers, and then erosion control blankets, which are tarps that are laid across the areas with slopes to prevent the topsoil from shifting. Below, I have examples of these three, as this first image is the silt fencing, the sound barriers, and then lastly, the erosion control blankets. Additionally, some BMPs will be sprinkling trucks, which spray water on the ground to help reduce dust control in the air. The stabilized construction exit, which reduces the amount of sediment on public roadways from the construction vehicles. And then lastly, the washout containers, which act as a storage and transportation device for harmful materials. For this first picture, I have an example of a spraying truck, which is going to be similar to the spraying system right here in this picture. The stabilized construction exit, and then lastly, the washout containers. Some pollution sources that we identified on site will be from the existing pollution activities and the expected construction activities. Those include the vehicles driving on the road, the paint striping, pavement operations, landscaping, construction vehicles, and then lastly, the demolition. Some possible improvements for Habitat for Humanity include adding a detention pond, a rainwater harvest system, and lastly, pervious pavement. For this first option, the detention pond, it stores unwanted storm water, and then later that water can be drained manually over time. Here's a picture of the parking lot with two proposed locations. Location 1 is right here on the top of this parking lot, and the second location is right here perpendicular to the Habitat for Humanity. I have an example of a detention pond in case anybody doesn't know what those are. As you can see, the sediment rolls, or the water rolls down the slope and collects here, and then over time it dissolves into the ground. The second option would be the rainwater harvest system, which would collect stormwater via gutters and then collect it into a tank, which then could be manually drained, which also this system allows for an option for the water to be filtered and reused, whether it's used for the toilet system or added into the plumbing so that it can be used for washing out any material that Habitat for Humanity brings to the site. The last option would be pervious pavement. Out of the pervious pavement, I decided to choose the pervious concrete, as it has a life expectancy of approximately 20 years, has a higher life expectancy than pervious asphalt, and it is cheaper than PICP, otherwise known as permeable interlocking concrete pavement. In this first diagram right here, I show a price of the PICP, the pervious concrete, and the porous asphalt. As you can tell, it's right in the middle. And in this top right picture, I have a picture of porous asphalt, which does the same thing as pervious concrete. As you can tell, with normal asphalt, whenever it rains, the water tends to make a pond and build up on the surface, while porous asphalt and pervious concrete, it dissolves into the ground. This image right here shows a better example of pervious concrete, as the ponding on the top, and then as it sits on the top of the pervious concrete, it dissolves into the ground, into the stone base, and then lastly into the soil. The recommended improvement out of these three options that I decided to go with would be the detention pond being the best option, pervious concrete being second, and then the rainwater harvest system being last. I made this decision based off the cost, the maintenance, the simplicity, and then lastly the aesthetics that would happen on the site. Now I'd like to pass it over to James for the hydrology and hydraulics division.
before I get started, I would like to show you the pictures of the site. So this is the back parking lot. It's close to the East Fifth Street, and you can see where the railroad is. And usually when it rains, it ponds like that, and the water stays there, and until it drains into Chadbourn. So those are one of the issues we have. The other issue we have is a culvert. This is an old picture I found on Google, but it's worse than this because the silt has accumulated there. There's also debris there that's kind of blocking the culvert. And the last storm we had, we were able to go there and take pictures and videos. This is how bad it is. And the other issue we have, this is the outlet of the culvert. So it has a lot of grass and debris and it's almost blocked. And when we went there, this is how the water flows. Okay, so before I get started on how we solve those issues, I would like to explain to you what hydrology is. It's a scientific study of things like infiltration, basically anything to do with the water cycle. While hydraulics on the other side deals with pipe systems and open channels. So the scope of the project has two main objectives: to eliminate the ponding behind the restore on that parking on northwest side of the building. Basically the parking that faces the loop. So we have to eliminate that water. The other thing we had to do was to deal with the water leakage into the basement, and Stephen did talk about that. Okay, and then so we had to do a drainage analysis using the rational method. And then some of the tools we use the City of San Angelo Stormwater Design Manual. We use a software called ArcGIS. This one right here, Hydro Tools, and that's a module that's in that software you use to delineate watersheds and do other things. We use Google Earth to calculate the surface of the water basins because ArcGIS had issues calculating that. And then we use HydroFlow module in Civil 3D for the analysis. And finally, we had to analyze that culvert to see if we can help the client deal with that issue. So previously, before the rainstorm, this is the watershed that we had delineated. You can see we thought the water came from all the way to the 14th Avenue, all the way to our study area. And we also included this area right here. And then we were almost done with the calculations and analysis and everything. And then the storm happened, okay? And then we realized that all the watershed delineation was wrong. So we had to redo it. Okay? This is what we came up with. For the area one, this area right here will be used to analyze, this is what we use to analyze the culvert. And the second area here, which is where the study site is, we use that for the rainwater catchment system. The first area, the size was 1.6 acres, while the second one was much smaller at about 0.7 acres. So this is the second area. So basically we took the area of one side of the roof and we calculated the runoff discharge, which was about 10 cubic feet per second. So on the other side, if you add that, you can see that it adds up to about 20 cubic feet per second. So the table you see right here, most of the data came from the City of San Angelo Stormwater Design Manual, and we had to input it into HydroFlow module in Civil 3D to calculate the intensities in inches per hour. And these are the values we use, because intensity is measured as inch per hour, so we use these values for the analysis. After we did that, we had to determine what the time of concentration was. What that is the time it takes a drop of rainwater to go from the remotest point of the watershed all the way to the lowest point. And these are the stuff we had to input into the program, the Manning's coefficient value, which was about 1.012 for the paved area, the flow length, and all these were added into to come up with a time of concentration of about 6.3 minutes. The next step was to make sure we were following all the steps necessary to use the rational method. And of course, we did measure the basin areas and define them. And then after that, of course, we found the time concentration and used the TR55 method based on the City of San Angelo Stormwater Design Manual. What this TR stands for is time release. I guess there were many other methods that they did before these. They realized maybe TR55 was better. They say the Stormwater Design Manual states that this method should be used for small basin areas in urban areas. And then after that, we computed the peak discharge using this formula right here. What BK is basically a coefficient. For the US customary unit, it's 1. If you were to use the metric system, this would be 0.28. The C is the runoff coefficients. These also come from the City of San Angelo Stormwater Design Manual. The I is the intensity and A is the area. So the program then gave us the peak flow for 2 years frequency, which was about 7 cubic feet per second. And you can see that the time concentration was about 7 minutes. And then we calculated the peak flow for 100 years frequency, which was about 12.2 cubic feet per second. And this is the flow we use to analyze the culvert. And these are some of the data we had to input into the programs. We had to tell the program how long the pipe was, what kind of culvert was. It was a box culvert made out of concrete, number of barrels. Although the opening of the culvert looks like it has 2 barrels, the other side of the culvert, the outlet, it has 1 barrel, so we decided to use 1 barrel. And then we inputted NAM, the Manning roughness coefficient. After we did that, we realized that based on the rise we measured at the site, the culvert was still performing okay. Although you can see a hydraulic jump here, that's probably because of the silt accumulation down there and other debris. It's still working okay. And this picture right here shows you where the pipe is. This is the opening, and that's the outlet right there, and our study site is right there. And then we decided to see what will happen if that culvert was partially obstructed. And we reduced the rise, and then so the blue basically is the water and the yellow is the embankment. So the water was not flowing right. The outlet control tells you that the culvert is not functioning as it was designed to do. So it's not working right, and you can see right here, when it rained, there was overtopping of the water. It almost ended up to the railroad track. And I'll hand over to Jeff for geotech.
Thank you, James. For our scope of work, it is fairly limited for our project since we are just going to be doing a soil report for our proposed parking lot and to do, to show our existing soil substructure. To do this, since we were incapable with our materials and our testing equipment, we could not go out and collect samples. So we acted as if we subcontracted out to SKG to do that for us. And so we have a report from them from a similar site that is nearby. So we took the soil report for the bus station depot from across the street from 2009. The soil substructure should be almost exactly the same. So we took that and we applied it to our site. So we have a clay loam for a distance down, and then it's capped off by some limestone, and there's no groundwater table present on our site. So it is very dense clay, and there's no water naturally occurring. And so this is what was calculated for our potential vertical rise as a worst case, and we have a type 1 or type 2 flex base based on the TxDOT specification as the City of San Angelo says it should be done. And so we'll be using a type 1 or type 2 as they say to specify it. And so what we decided has been to compact it to 95%. That's supposed to be, 90% of modified Proctor test for the subgrade. So the existing soil, 8 inches down, has to be 90% modified Proctor. But this exceeds the COSA specification of 95% of the standard Proctor, since the modified Proctor puts more energy into compaction, so it should exceed that requirement. And we're going to say the same requirement for the flex base, so the fill material that we're going to use to grade and bring up that bowl that you see on site, that's going to be a minimum lift height, or maximum lift height of 6 inches, so that's going to take at least 2 lifts to get up to the required elevation. We're going to do a 90% modified Proctor again, which is again greater than the 95% of the standard, but also the maximum lift height is lower than the city specified one, which is 8 inches. And these are going to be in items 247 and 200 for the subgrade compaction of the design code. And so for some of the design references, we just referenced the soil report for the bus depot and wrote our own report for our project and our needs. And then we referenced the COSA design and build specifications. All right, and then for transportation division, I'll take care of that as well, since we're going to be, it was dependent on that. So we analyzed several different design options for the materials, what would best meet your needs. And so we have concrete, a caliche base as we have, like what we have now, or asphalt. So we decided on concrete since it has a high upfront cost, but it has low maintenance costs. And so the life cycle cost is going to be cheaper, it's going to last longer, and it's just going to fit our needs a lot easier, especially with handicap parking getting on that side. That's going to be better than the caliche base. So we moved forward with the concrete design. All right. So when we went and did our site survey in our analysis, we did a survey from a point right off screen right over here, and we found these data plots as our elevations. It looks very, very level, but there is a low spot right here, right through here, of our proposed parking lot. So here we can see our proposed parking lot, and where that bowl meets is right here. And so what we did was we're going to raise it up right here and have a 2% grade off to the side to where we're going to have a COSA specified dimensioned curb, which will run off into the street so that we can move that water away from the building and away from the parking spots. In here we can see our layout for our parking lot. So we have the handicap spots. As ADA specifies, they are supposed to be 11 feet wide. And right now we have them set at 12 feet wide. So they're a little bit wider, a little bit easier to get into. We have an 8-foot section right here and capped off with a loading dock. So these were our main deciders on how to lay out the parking lots. We wanted these close to the ramp that they're going to be using. and we wanted this to be right in front of that door, that garage door that we're gonna use to offload into the restore. And then after that, we have a bunch of, I think these are 10-foot spaced parking lots. And some of them are super long because we know you are going to have lots of pickup trucks that come and stop for loading. And so we have some pickup truck spots for anything with like an extended bed that might be used for hauling, just to meet your needs. All right, in here we have a reinforcement plan for the concrete and a joining plan. So anyone who's worked with concrete can tell you that concrete likes to crack if you have long periods of it that don't have joints. And so this is what we propose we do our joining plan is. So for a 5-inch slab, we're going to do a 12.5-foot long piece. And so as per, the Society of Reinforcing Concrete Reinforcement Society, they say they give a formula for that, and for 5-inch concrete, reinforced concrete should be 12.5 feet. And so we adhere to that. And so we'll also split it down the middle so that we don't have any long cracks down this section. So if it does crack, it's going to crack on one of our joints. That way we can predict it and we can model it. And so we have our reinforcement for this. This is mostly for temperature control. So as the temperature changes, concrete it contracts and it expands, right? And so if it does that unevenly, it will crack. So we have this reinforcement plan. So it's gonna be number 7 bars on 18 inches on center. And so that way we're not putting a bunch of steel into it, but we're making sure it's not gonna crack on you prematurely. I'm gonna hand it off to Colin, who's gonna discuss our structural division.
Hello, my name is Colin Baggett. I did the structural analysis portion on the building. And to give you an idea of what the building is like inside, in this bottom right corner is a picture of the basement section. You can vaguely see some of the cast iron columns here, and then there are hot rolled steel beams set on top of them. This is a picture of the first floor. This area is open, and then in the center of the building there is a second story that is also supported by cast iron columns and hot rolled I-beams. And this is the second floor, which is basically a storage area, and you can see the layout of the trusses shown here, supported on wood columns. So initially we had to go into the building with tape measures and basically find the dimensions of everything. There were no existing plans. The building was originally constructed in 1902, we believe. That's the nameplate on the front of the building, and the materials date from about that period. The columns we found to have 3/4 inch walls. We had to also find the layout of the building for a 3D model, and in this floor plan on the right, you can see 3 columns that are starting to get corroded on the bottom, which we'll discuss in a minute. So the scope of our analysis was to address the structural integrity of the columns that are corroding, and to address deflection on the floors. So the floors were moving under pallet jacks. It kind of seemed that they were soft, but we also wanted to make sure it wasn't structurally, going like it wasn't going to break through the floor because the structure was weak. So instead of doing the analysis by hand, we decided to use robot structural analysis, which is Autodesk's software. And just learning the software was challenging. I had started building a 3D model of the entire building, and for simplicity scaled it down to a cross section, which is 10 foot wide, or the columns are set on 10-foot centers here, 16 feet wide, which is similar to the building. These would be the hot rolled I-beam spanning the columns, and then this part of the structure is all wood. Once the analysis was performed on the cross-section, the results could be interpolated to the rest of the building, given that it was symmetrical. Another challenge was being built in 1902. The materials that we use in the modern world are not equivalent, not the same as materials used at that point in time. Dimensions have changed, resources have changed, the source of lumber, the source of steel. We did our best to match them up with equivalents in the structural analysis software. This table on the left side, you can see some of the materials in the building, and on the right side, these were the equivalents that we came up with. Using these cross-section drawings here was essential to identifying the materials and equating them to modern equivalents. So this picture down here is actually of the original model we started with. It is more or less for demonstration. We didn't actually use this model for analysis, which was of the entire floor. We used the cross-section. But it shows the tributary areas we use to calculate loading. There's different ways to put the loads on beams, and essentially these colored stripes shows half of the load on each side of a beam being placed on that beam. And then the red arrows show a uniform load that was placed on top of the beam. We did do an analysis with this with just a rough number of 2,000 pounds per square foot placed on the beam. It didn't show any deflection, but that wasn't part of the final results that we reported. Also, floor joists weren't included, and the type of flooring used wasn't included. The goal was to analyze the structure of the building and how much weight it could hold, not whether a floor joist would break or a hole would be punched in the floor. We also had to define loads for each section of the building. On the first floor, we used ASCE 7, which is kind of a standard for structural engineering. Applied them as 125 pounds per square foot. On the second floor for the storage area, we approximated 60 pounds per square foot. And on the roof, a common load for asphalt shingles and decking is 15 pounds per square foot. Since we left out the cladding, the decking, and the joists and rafters, we went ahead and doubled the 15 pounds per square foot on the roof to 30 pounds per square foot, and could finally run the analysis. These are some of the results that came back. This figure in the bottom left shows the loads. They're represented in kips. A kip is 1,000 pounds, and so each of these columns roughly has a reaction of about 5,000 kips. So there's a support load from the facility's normal use of about 5,000 pounds on each column. And this figure up in the right shows the deflection, nodal displacement or deflection. It's how far the nodes move. We did get this number of 1.2 inches, which is a lot, and I think that's an error in the model. I just ran out of time to chase down the error. Our average deflection for most of the other joints was less than 1/10 of an inch, which is expected in a wood structure. To address the corrosion on the columns, once again, they're marked on this floor plan of the basement. These were the 3 worst ones. However, the entire structure, being over 120 years old, has corrosion on it. And taking the analysis we did, finding a 5,000 pound reaction, we added 3,000 pounds for unaccounted weight, which still gives us 8,000 pounds per column. On a table that we found from 1926 in the Chas Wade catalog, they had the 1/10 breaking strength of cast iron columns listed. And for our column with 3/4 inch walls, a 6-inch diameter, 8 feet tall, the breaking strength, the 1/10 breaking strength is 27 tons, which is about 56,000 pounds. And so if you find the actual breaking strength, which is 10 times more, that's 560,000 pounds per column. Taking that information and the table that we found, we reduced the wall size of the column from 3/4 inches to a 1/2 inch to account for the loss of material to corrosion. It still showed a working strength of 23 tons, which is 46,000 pounds, and significantly less than the support of 8,000 pounds that came out of our analysis. So the conclusion we came to on the columns is that the way they are structurally, there's no issues. However, the corrosion does need to be addressed. So the remediation for that would be mechanically removing the rust with a wire brush or some type of abrasive sandblasting. It could be treated with phosphoric acid to neutralize the rust, and then you paint the steel structure. It would prevent any further corrosion and last for at least 10 years, if not longer than that, before it needed any type of maintenance on the painting. These were the historical documents we found. So the hot rolled I-beams came from Illinois Steel. They were stamped on the side. This document's from 1914, but other records showed that the structural light I-beams used in the building dated back to, I think, 1896. So we're pretty sure that this diagram is the I-beam in the building, and it was the actual beam that we had is on a separate sheet that's listed in the report, but the diagram was more interesting for the presentation. And this is the table of 1/10 breaking weight in tons for cast iron columns from 1927. I don't know when they quit using cast iron. So the disadvantage to cast iron, if you're not aware, is it's really brittle. So it has a great strength until some type of flex happens, and at that point it snaps. Whereas our modern steel has more ductility and can flex when put under a breaking load. Like basically it'll give us warning before something just snaps and collapses. We know that it's coming, and we can at least try to address the problem before it falls down. Whereas cast iron, you don't get that luxury. For a wind analysis, like on a very extreme scale, figured like an F4 tornado, which is 175 mile an hour winds, which is 250 feet per second. It was simulated on the y-axis, so you can see that the y-axis would be in this direction. The x-axis is on the end of the building. So this simulation is the wind blowing in the positive x direction, which would be north-south on the building. The actual uniform load on the side of the building would be about 1/10 of a kip, which is 50 pounds per square foot from the wind. And the numbers represented here are displacements. As you can see, there's a displacement of like 12 inches, so it means that your wall is going to move 12 inches, which is pretty bad. So the recommendation for like dealing with a tornado situation would be to put anything valuable in the center, because the walls are probably going to break. Or the basement, which is a great place to keep stuff that you don't want a tornado tearing up. And finally here, that's just a picture of the nameplate on the front of the building, 1902, Martin Oliver. It was a grocery warehouse situated on the side of the railroad tracks, so boxcars could come in, unload, put cold goods and dry goods here, and then distributors could pick them up and take them wherever. This is another picture from the basement of the hot rolled I-beam and the cast iron columns, and you can just kind of see the corrosion from time that's building up on those beams. And a list of the cost to, the minimum cost we found to neutralize the rust in the basement and paint it would be about $5,000. The solution to the soft floors, there is no structural problem, so you don't have to worry about the building collapsing under a load. But, so the solution would be new floor, like deck the floors with plywood, and then you could go with a new type of flooring on top of it, or just leave the plywood. The neighbors, the Hartman Roofing Company has done the same thing, and they just have exposed plywood, and it seems to hold up to their forklifts on top of it, which is about 15,000 pounds on a loaded forklift. And then, yeah, the final recommendation doesn't cost anything, but keep your valuable stuff away from the walls in case of a tornado. So I'll pass it off to Jeb, and he'll bring us to the end.
So we're just gonna run through the structure, the construction division real quick. So most of this is going to be limitations and constraints, and then a cost analysis for each of the components for your improvements. So, well, one is just gonna be this design for your ADA ramp for your restore side. We noticed that you stated that you would like access on that side, so you wouldn't have to keep that back door open and then wonder if someone wanders in. So here we would then say chip out that, use a chipping hammer to have someone take out the porch out on that corner as we discussed before. So this is gonna go out, there's 4 foot and then 28 foot and then another 4 foot, which is going to make up the whole of that distance from the stairs to the end of the building. And so we have a 114 slope all the way up. You can turn around and come back. And so we're gonna meet ADA standards, and that'll be well within our allotted space. Because we have a total of 36 feet, which we're going to take advantage of fully here. So we have 36 feet across and about 8 feet right here. So we're gonna meet that requirement with this design. So moving forward, we have the cost analysis for that. Just for the demo, about 300 man hours, and for any construction company, their rate is gonna be high for man hours because 1, they have to pay the employee, 2, they have to pay all the insurance and everything else, so it costs a lot per man hour. And so that's going to be an expensive project. Yeah. And then for the parking lot, that's going to be for all of our fill material, all of our concrete, and then our equipment. This would be the breakdown of this, and both of these should be in the report that we will turn into later. But this includes the materials, so base material, concrete, machinery for the days that we're going to be using them, then the compaction for the base and fill, the concrete, tying, pouring, waiting for it to set, and then the testing of the concrete and the proper materials, as stated earlier. So permitting, in addition to the ones that Stephen had previously outlined, we're going to have a general construction permit from TCEQ, the lane closure, so for anything that's gonna be offloading, we're probably gonna have to shut down a lane of Chadburn and organize traffic around that. And then the contractor registration through COSA and the concrete testing. And then here's some references that we use throughout the project. So it's gonna be TxDOT, ASTM standards, and then the Reinforcing Steel Institute. Yes, sir.
I have a question for Colin. In one of your slides, you said there was a number 1.27, but you felt like it was perhaps made in error. I just wondered if,
So
yeah, right there.
This figure in the right is from the structural analysis with all of the loads placed on it as well as the safe self-weight of the structure.
Okay,
So these numbers represent how far these nodes would displace under a full load.
okay, so it has nothing to do with the area of the building, or, okay, specifically, my question is that where that freight elevator is located?
No, so
Okay.
the elevator shaft wasn't included in this analysis.
Okay.
I would consider this more of a preliminary analysis to get a general idea of what the structure is capable of.
Okay,
To do a full detailed analysis, the whole building would have to be modeled in detail, which would include the elevator shafts as well as the stairwells
okay,
and,
gotcha.
So on that same slide, why do you have two red things and a green thing? You got another one that's a displacement just as high and it's not marked. What's the coding on there? You got two displacements that are in red, one of which is a 10,000th of an inch, and you got one is 1.2 inches, which is in red, and you got another 1.2, which isn't in red, and you got a zero that's in
so
green.
this was my first time using this software and I don't have an answer for that.
Okay.
Okay, go back to that. When it says the 1.27, where is that on the structure? Where is that? Is it at a joint? Is it on a beam? Where is that at?
I believe the 1.27 is this
Right
joint
there?
right here.
Okay.
I think it's an error in the model. I really don't think that's the actual displacement.
I hope not.
It's something to do with how it was drawn out. If it was, the building's been there 120 years, you would know it.
Yeah, okay.
Yeah.
Gotcha.
I'm just a little concerned about the tornado, because my office does face the north, and I have a window right there, so it's gonna fall in on me.
Yeah, go in the basement.
Just leave.
Or leave.
I mean, and we know that those things happen because of the warehouse collapse that was just a couple of blocks over.
Right.
When the I think that was straight line winds that came through.
Yeah.
We did suffer some damage, but it wasn't,
So what was surprising is like an F4 tornado's big.
yeah.
And most of the displacement on the building was, like not significant. And these numbers are limited to like significant figures. If I had put them all on there, you couldn't even see the model because every number and every displacement in every direction comes up and it gets really complicated to see.
So you said you used an F4 tornado. What is the code design load, wind load for this? Is that the code load, or is that just one you picked because you thought it was interesting, or?
I thought it was interesting. I kind of ran out of time on the wind load thing. The structural analysis was the main focus, and we're coming down to the end of the project, and the wind was simplified for that reason.
Because I'm thinking it's like 120 miles an hour here, but I don't remember.
Oh, here?
Yeah, the design.
I think the design is 100. That sounds right. I know in Miami it's 160. In places like with hurricane winds, it's about 160. And there's a factor of safety in that.
I'm pretty sure that's not the design wind load for this, but you'd have to look up the code. I think it's like closer to 120, but I don't know.
So you did these on partial drawings, do you think that affected your scores any? Are you confident in saying that the whole building is safe even though you only did a partial structural analysis?
So for the sections that are represented by geometry, like symmetrical geometry to the sections here, I would say yes. The loads were applied in the Z direction, which is straight down. It didn't account for any loads, coming at an angle, which shouldn't happen in a normal situation, just for storage. And the stairwells and the elevator shaft weren't accounted for either.
Right.
But essentially, if you took the building facing Chadburn Street, and assume this to be the front of it, the structural support that's holding everything up you could multiply this 9 times and stack them together and have the full geometry.
So what are the limitations of your analysis? I
There
think
are
that's the
lots.
question.
There are huge limitations. I
Okay, so
used-
so give us the top limitations.
The stairwells weren't included, the elevator shaft wasn't included. The cladding was assumed to, have no deformation, meaning that stuff like floor joists that are set on 12-inch centers and the flooring and decking on top of them was not included in the analysis. Some of the material equivalents were, they're close, but matching like cast iron to hot rolled steel works to a certain point, but if deformation comes up, then you're dealing with a different breaking strength at that point. We weren't even approaching the strength of the column, so I don't think that would be an issue. You know, including wind load in with the dead load of the building and the self-structure weight, like going into a proper detailed structural analysis was beyond our abilities as students at this point. It could be completed if there was concern. But at this point, with the light-duty warehouse classification, not having a significant amount of weight on the floor, it doesn't seem that there's an issue.
Do you have recommendations for operating loads for the client then?
Like, 125 pounds per square foot is what we factored the loads with, so that would be a pallet jack, a full pallet of materials, like a pallet of paint, shelving, eye-level shelving. 125 pounds is over the loads that are on the retail space now.
And what about the second floor?
The second floor is
I forgot what
almost
you used for that,
empty
you didn't
now.
use 120 on that, right?
No, I use 60 pounds per square foot on the second floor, and that was really an estimate. It's the same load that like this seating space would be
Like, we could-
analyzed at,
Which could be pretty low for a warehouse is why I'm bringing it up.
which would be low for a warehouse, but the only way to access the second story is through a small stairwell, and what's stored up there now is, there's some light lumber and like decorations from parties and things about it. We had even discussed demolishing the second floor, which is what they've done in the Hartman Roofing building, to open up and allow taller shelving in the retail space. So, the use of the second floor, it was approximated, but it's not used in reality. So, I don't know if that,
I was asking if you could, the question was, do you have recommendations for the client on limitations for loadings?
yes, like next door, they're running a forklift with 3,000 pounds, 3,000 pound rolls of steel on it. It's probably about a 15,000 pound load that they're putting on the floor. They don't have any issues now. In theory, the columns and the I-beams shouldn't be a problem, but I wouldn't recommend you driving a forklift in there without having a more extensive analysis done. We were hoping to get the answer to that question from this one, but our abilities and time were limited.
Okay, your turn. Go to the slide where you had the concrete with the splits in it, with the 12.5 foot.
The expansion.
Yeah, the expansion part.
At the very end.
Right. We passed it.
This one?
Nope.
Yeah.
Right there. All right, you got 12.5 foot in a vertical direction, but 20 feet in a horizontal direction.
Yes, sir.
Why? I mean, if 12.5 is what is needed to stop the cracking and everything, why wouldn't it crack in the 20 feet that is in between that one and the edge?
I don't know the answer to that. It just usually, it doesn't crack in squares, it cracks in rectangles. And this is just like a rule of thumb that has been learned over like time and use of concrete.
Okay, but if I remember right, you said 12 and a half was the minimum. So would that not be a minimum 12 and a half foot squares and have another column running down and split that instead of into 2, into 3?
No, I think it's just the 12 and a half for that one spacing. This spacing was not outlined in the document, in the requirement. It was just this spacing.
Okay,
Is there a theoretical reason why you'd have different spacing in one direction than
yeah.
another?
Not that I could find in the specifications that I found.
So in the specifications you found 20 feet is acceptable between one
It
another?
doesn't say in different orientations, it just says that at least you need the 12 and a half spacing for that direction, for one direction. It doesn't say how to orient it.
Okay, do you see where I'm coming from though?
Yes, I do.
So there's no fair answer to that right now?
No, sir.
Okay, well, that's what we'll go with then. On the other one, when you did, I was gonna ask you about the soil makeup, and you kind of touched on that.
Yes, sir.
For the clay type that we have, for the geotechnical, we have, the clay loam and limestone.
Yes.
Okay, whenever he was talking about the pervious,
Concrete.
concrete, it soaks down, and in his model that he presented, at some point, it soaks into the soil.
Yes,
It does not run off.
yes. So it acts as a reservoir of sorts.
So
As
the
it
clay loam
drains.
does?
The clay loam does not drain quickly.
Right.
So clay has a really low hydraulic conductivity, so it holds it for long periods of time. So in the fill material and in the pavement, you'll have space for some of the water, but most of it's gonna run off, some of it's gonna stay, and it's going to drain slowly through that clay loam.
Okay, so the fill material that we're talking about, and I didn't understand what Proctor meant.
The Proctor is a compaction test to make sure that you have it stabilized correctly, so it doesn't potentially settle too much
Okay.
under any load.
So part of the purpose of that fill material is in a certain sense, it's gonna act as a reservoir. It's going to fill up with the water
Yes.
to hold it, to come off, and some of it's gonna run off,
Yes.
My question for that is because of the way this building is built and the issues we've had with it, the piezometric pressures that are gonna build up when the water goes into the clay, would that be monitored in any way, or would it be far enough away from the building that the piezometric pressure is not going to push in and cause deformation of the basement walls?
It wouldn't be measured, no, I did not account for that.
That's a good question.
That is a good question.
So,
I didn't.
Is pervious concrete used much? You may not know.
It's not very common, no.
In San
Well-
Angelo?
in San Angelo, it's
In
not
San
very
Angelo,
common.
it's not.
In San Angelo, it's not very common.
No.
So, but I wanna go back to Stephen's presentation, right? So, and I realize you're not you don't need to present anything, I don't need to see anything, but I realize you didn't recommend pervious concrete. But the reason you didn't recommend it had nothing to do with its performance. And so when the water infiltrates through the pervious pavement, where does it go?
It's supposed to go down into the,
Yeah, it doesn't dissolve, by the way,
Right.
it infiltrates, right?
it infiltrates.
Infiltrate, dissolve, not the same word, right?
Yes, sir.
Okay. And how's it gonna, and what material is it gonna be infiltrating into if you're gonna use that here? This is the point of this whole discussion, right? Where's it,
Into that clay area.
yeah, but except, what's the problem with that?
Is that clay holds water.
Yeah, it's not going to infiltrate, right?
Right.
So, I'm glad you didn't recommend pervious concrete, because it's not gonna work, because you can't get it into the ground.
Right.
That's the whole point, right? So, and then, if you are putting it next to the building, you do have the potential, particularly if you got a clay soil and it's gonna shrink in the hot weather, to open up a very small crack, it doesn't need to be very big, and then you now are going to have a large piezometric, or I would just say hydraulic pressure on, against the basement wall, and it's probably more of an infiltration and leak and damp problem. So the question is, what are you doing about that?
About resolving like.
Preventing, I mean, you sloped away from the, you're designing a sloped away from the building.
Right.
That helps. But when you get the 100-foot storm and somebody hasn't cleaned out the culvert and it does back up, what's to prevent it from rising to the point where it does?
To clarify, the culvert has nothing to do with the building.
It's access
That
to the
was,
parking lot.
that
of
was
the building.
analyzed separately to
Oh, I got a question
satisfy
about that one
AMET.
too, because I obviously didn't understand your presentation. But anyway, what's to prevent infiltration into the basement?
That's multiple things. One would be redoing the grade in the proposed parking lot.
That helps a lot.
The second thing would be an alternate way of changing where the stormwater would be, whether it's to the detention pond or to a rainwater harvest system.
So most of the water that comes into that loading dock area where it does run down that wall,
Right.
it comes off the roof as
Yeah.
it is now. So if
Okay.
we do improve a rainwater harvest system, then it will capture that water and put it in a detention tank where we can let it off manually rather than have it run straight down our wall.
And soak in the bottom.
So it's not paved currently, and there's no infiltration problem in the basement.
Right.
Okay. Well, another, whatever pavement you put in there, you need to have a good seal, you need to have a good
Yes.
mastic between the wall and it.
Yes.
You presented the pervious pavement, the detention basin, and the rainwater harvest system is all analyzed to do the same, to solve the same problem, I guess, because you compared it to each other.
Right.
How do they all, what's the problem and how do they all, because those are two, those, at least one of those systems doesn't, in my mind, do the same thing as the other two, so what's,
Well, based off the cost, I chose the detention pond over the other two because it'd be cheaper to install rather than.
yeah, but that's not the question I'm asking. The question I'm asking is, how can you compare those two things? Do they all do the same thing? What is the purpose of those three, systems? And I mean, why would you recommend any of them? What's
I
the purpose?
recommend them to help reduce the stormwater that's building up on top of the site right now that's causing the
Okay,
pond.
so how does the rainwater harvesting system do that?
It allows the gutter system from where it is now, where the water just pours onto the dock and comes down the walls and then sits in the parking lot area to be, I guess, collected and sent somewhere else, whether it's the gutter system sending it to the detention pond itself or to the rainwater harvest system tank, which should then later be manually emptied at a rate whichever was needed.
So the harvesting system is just a different place to put the runoff?
Correct.
How large, did you calculate the size of the tank that's required to do that?
It'd probably be around 60,000 gallons.
Big tank.
That's a big old tank.
Right.
And then, and is it a harvesting system or is it just another detention system? Because those are two different,
Well, that
those
was the
are two,
options that.
those are two completely different separate things. That's why I'm confused.
Right, and that's one of those where it depended what Habitat Humanity wanted to decide with that. If they wanted to make it to where they could reuse the water in the tank, that would mean that it would be a more expensive project, because then they'd have to pay for the filtration system, and then also have to redo the plumbing on the actual structure itself, so that the water from the tank could be distorted and sent to throughout the building.
So what would be the use of the harvested water?
The harvested water could be used for anything, whether it was, if they filtered it, then it could be used for either the toilet water to help reduce their water bills for using the toilet, and then also if it was filtered thoroughly with a more proficient way, then they could actually use it to clean any of the kitchen material that they get brought into the store or anything, because most of the material
So
that's
those
brought
are
in.
two different, I mean, are you familiar with the classifications of you're talking about two different water quality and for two different sources,
Right.
you know the difference between,
As far as classifications, no, but as far as the pricing, yes.
so did you price water treatment for purple water, which is the non-potable? So one of those is the non-potable use and one of those is the potable use, right?
Right, and the potable.
Did you price, in your systems, did you price treatment into that, or did you or are you just the tank holding it and they're gonna just discharge it?
I considered it both. The reason why I made it the last option out of the other two, or the other, all three, was that I was assuming that they would use it as a reuse, which would increase the price of the system, and also,
Potable or non-potable?
it would be potable,
So you price a potable treatment system in there,
yes.
okay? That would be very expensive.
Right, and then also with that's why I also added simplification, or simplicity into the factor, because it'd be a hassle to have to redo all their plumbing, and I'm not sure that Habitat Humanity would have that at the top of their list right now.
Good, well, that makes more sense. I'd like to, well, I don't wanna ask questions until somebody else does, I got lots of questions.
On a similar line of thought, I think the detention pond was missing in the hydro part. I realize that. And I have a question for James. I was driving the other day from the loop into Chadbourne, and I happened to see a second inlet into what it seems to be the same pipe, but I don't know. So that's why I wanted to ask. This additional inlet to the culvert was just a few dozen feet to the west, to the right.
Yeah, there is another inlet there, yeah.
So why would there be a second inlet in there? Is there connected, not connected? What do you think, based on your observations there at the site?
I'd say that it's
Yeah,
different.
I'll say, if that other inlet conveys the water.
Can you put a site plan so we can, as we're discussing this, cause I got a bunch of hydraulic questions too, maybe the purple drainage basin one's good enough, yeah.
Yeah, that was,
So the second culvert is somewhere here. The other opening is somewhere here. The one we analyzed is here. So if that second inlet conveys water over there, I would say they are connected. Yeah.
So I'm really confused about the two well, if I understand this right, one of these catchment areas here is just the roof, right?
Mm-hmm.
Okay, and that's not, but what's leading to the parking lot getting inundated? Which catchment is the parking lot in?
Only area two, there's a railroad track and a large
Okay, all right,
embankment
that's-
separating the
okay.
two.
So
they're-
the parking lot inundation is only coming from the roof?
Yes, it's coming from this
So
side
not,
of the road.
and upstream is which direction in this?
Yes.
So down.
Well, but within the parking lot catchment, cause you got a big, the railroad's separated into two catchments,
Yes,
right?
yes.
How far back does that catchment go? Cause the upstream is down to the left there, right?
Yes, so
Yeah.
this one leads.
No, the one that's affecting the parking lot. Is it only that, or is there anything upstream from it that's flowing into the parking lot?
It's hard to tell.
I think
It
it's
should be just
only
this.
this one,
Really?
yeah. Was, let me
Well,
see.
you did the survey, you did the level survey, does it, so the rest
We have
of
a-
those buildings and all that stuff on south of the railroad, none of that other stuff drains out to the street in that direction?
I mean, I
Yeah,
have an
because
answer for
right,
this.
right here,
Yeah?
Hartman Roofing has a fence built up where they raised it up a little
Okay,
bit, so
alright.
it drains.
So that does separate your catchment,
This road right here
yeah?
drains this portion. It comes down this road
Okay.
into Fourth Street and then flows out. to
Okay, so
Chadbourne.
that is separate,
So,
okay,
so this
Most of
is
it just
actually
uses
the
it.
catchment area.
right. And so you're addressing the drainage on the north side of the railroad, is that part of the property, or did you just do that because you needed more hydraulic scope in the project, or?
That's it.
I'm not complaining about it, I just wanna know why.
Yeah, so basically, this one.
That was too simple, and Dr. Pignon said you gotta do something more complicated.
Yeah, you're gonna.
Let's
do
look at
that.
those other problems there, okay, that's fine, I have no objection to doing that, I just wondered, now, what I don't understand is how you got from can you go back 2 slides, I
Well,
think?
it is important, the client did mention all of these problems, so.
Yeah, that's
now-
fine.
Now the client knows that the flooding that's occurring is not really affecting your site.
Right.
Yeah.
The
Just
city needs
affecting
to take
people,
care of
yeah.
that.
Yeah,
part,
yeah,
is
yeah,
what
you
they're
gotta,
doing.
yeah, you gotta call your city councilman.
But I didn't know.
No, I'm not
if the
complaining.
Yeah, well, I didn't know if the water was coming from the roof,
Right,
because the water does run down off the roof, down the side of the building, and so structurally,
yeah,
in the basement, I mean, just seeps through. But it holds water for so long, and that
yeah.
all of that holds water, so I didn't know
No, that's great to find out.
that, yeah.
Yeah.
If
I'm not complaining
the
about that at
railroad
all.
tracks probably catches a lot of it and keeps it
I'm just,
kind of right
so I
there,
wanna know
just
how you
so
got
close to
from
empty it.
this catchment to the 1.5
The small
acres.
one? Okay,
I mean,
so-
'cause I mean, that's a big, it's not like, oh, we adjusted, I mean, it's like, that's like huge, so.
That's
so-
automated.
So, I mean, how did you get this one in the first place, and then how did you end up with the second one in the other place? Cause that's
So-
like, you know, I mean, I understand corrections, but holy smokes.
So for this one, you
Right.
first have to get the digital elevation models from USGIS.
Right,
And then after that, you have to draw the contour lines that will
Right.
show you where
yeah,
the
yeah,
water
right,
drains.
I understand all that.
So these was drawn based on where the water and elevation was leading the water to.
Okay.
And then the second one, we went on site when it was raining to see where the water was coming from and where it was going. So this was drawn because most of the water was coming from the parking lot, from the bus station, all the way into Chadburn, and then the intersection of East Fifth and West Fifth, right here. That's where most of the water was going. And then this water right here, most of it came from the roof.
Yeah, I got that part.
Yes.
Go back to the other one first, go back.
If I can add in there, because I use these systems in the in the hydrology class, it's typically the watersheds that we analyze are like 100.
Yeah, like a
50.
teeny watershed.
Yeah, it's so tiny that the model has a foot of error everywhere, especially in the elevations. So it did not capture the subtleness of the catchment, of
So-
the small catchment.
So my question is, what's different about, where's the mistake in this model? If you're correct in that catchment for that, I mean, I'm surprised that there's not more upstream to the southwest in, that's feeding into that, and I think that's the same question about the other culvert, right? So, what's wrong with this, you know, what's the feature that you're not capturing in this model that separates that other catchment? Because that other catchment is like, it seems really way too small to me, but I don't know. I mean, I wasn't there, so.
Well.
Because you cut off a huge amount of the, right? You cut off
yes.
I sort of understand the stuff to the north there, because I'm suspecting that there's some stormwater management around the loop that's gonna catch that part of it, but I don't know. But I'm really surprised that the catchment you got along the railroad to the southeast got cut off so much in your actual model. Do you understand what and I think it's
Yeah,
related, I think it's related to the same question Dr. Pignon asked about the other
Yeah.
inlet, right?
Yeah, I understand your question, because this is like 14th Street. Before the water gets here, it has to go through some other systems that convey water somewhere else. And we have a loop here, the water from the loop must go somewhere. And when we drove there when it was raining, we drove around this area and we realized that most of the water over here doesn't come back to the site. And also this water doesn't come to the side. Some of it goes away, and then this small area right here is the one that leads into the study side.
But that realistically could be the catchment for, so, I mean, you're at the top of the catchment area. If you consider this a separate catchment area, as south of the railroad tracks that divide it, like if you were finding a point down here, that realistically would.
Well, I
be the
understand, but then it
catchment
would,
area.
but that wouldn't have been, I mean, then there's a big mistake in your first model, because you're at the
Yeah, there was
higher
this
elevation, right?
mistake was
I'm-
like.
I'm just trying to understand,
automation.
this is,
Like you hit a button and it
Okay.
tells you and it was wrong.
so when you showed me this catchment, I went, that seems weird. And then when you showed me the one you ended up with, I went, okay, well, I think you're going the right direction, but I wonder if you didn't overshoot it, right? And observing one rain event, that was a big rain event, well, it wasn't it wasn't a 10-year storm, right? What was that, what was the return period of the storm we got?
You should have put the video in here.
Yeah,
That was-
well, how many inches did we get that day? I mean, I don't know how many I
It was
got.
about a 3 to 5 year.
Yeah, that's what I'm saying, it wasn't your design storm, right?
Yeah.
Okay, so, I'm just thinking, I'm thinking your pink catchment areas are too small, but I don't know.
Well, also, I didn't do this alone.
I don't,
So,
I just don't think that's the complete catchment area.
So what I'm saying is the whole team,
I mean, especially given that St. Angelo's are,
yeah.
we have so many problems with storm water already, I don't think you got the catchment, so Bill, get your opinion, I don't think you got the catchment area right, so,
Okay.
all right?
If I can, also,
We got anybody else, any other practicing engineers wanna pipe in on it?
Russell,
Oh, Russell's there, hey, Russell, what do you think?
Y'all are doing a great job of grilling them.
he mentioned something the other day, he called sub drainage system. Means this is a small drainage of a bigger drainage.
Right.
So probably that pipe was not a culvert, but a storm water, a drainage pipe, a storm sewer
Yeah,
with multiple outlets. So what that mean is that there's another catchment contributed to the same pipe upstream to the west.
Yeah.
So maybe it wasn't a culvert at all, maybe it was a storm drain, pipe. But though your conclusions are not incorrect, just that we need to add an additional piece of flow from another upcoming upstream
Stream,
drainage.
yeah, your analysis is, there's nothing wrong with your analysis, and you point out even with this catchment area, there's a problem, which the residents already know. So, but I don't think you got the whole catchment in it, right?
Okay, on area 2 down there, that's the roof. So it's actually split in 2, and so one goes that way and one goes this way? Yes, this side ends up into Chadburn.
Yeah, we use the actual area, it's just exaggerated.
Okay, exaggerate, okay, go to the slide where you calculated the cubic feet runoff.
Yeah, you got the, yeah.
This one for area 2? Yes, okay, so there's your area, so you're, okay, at 0.8 inches per hour, you're talking about 10.4 cubic feet per second?
Yeah.
Yeah.
Yes.
Yeah.
This, yeah. So basically, this is the intensity, that's like 0.8 inches per hour, yeah. Okay, well, on that particular day, we got more than that. I think in that area, it got not quite 2.5, maybe 3.5 inches of rain in a very short amount of period of time. So we're talking about, let's for easy math, let's go with an inch per hour. So that's 3 inches per hour at 9,000 feet per second. That's a boatload of water that comes off of that. So for all of that to go into that small little parking lot area, and it got nowhere to go once it comes off of that, yeah, that would account for all of that water that we see, it's just that.
Right. Yeah,
It
and-
just sits here and probably some of it ends up here.
Cause it's gonna overflow that basin. that-
Pretty quickly.
It's flowing into
And-
Chadburn, so it
and-
gets full.
They can't use their apartment roofing, it's like a swimming pool behind that part of the building. When we had water in the parking lot at Habitat, they had a swimming pool next door. And one of you saw that, and it was there for a couple of days. So, I don't know if there's that much difference in elevation, but the
So
water stayed around.
this elevation is lower than this one.
Yeah.
So it's just, the pooling is right here, it's just most of the water sits here and for a couple of
If
days.
you pave it and it drains into Chadburn, like, that's the solution.
Yeah, that's what you're
It's a
saying,
really
so-
easy solution to it.
Yeah, with the paving and then
Is
the
that-
sloping we're talking about and the buildup and all that kind of stuff, this goes away.
Did you analyze that? Can Chadbourne drain it? Or is it just gonna back up on Chadbourne?
That's not their problem anymore.
No, it is if it doesn't drain it, right? It's not-
If you do it on weekends or after dark, we got no problems.
Yeah, you
My
can
question is,
downstream
can Chadbourne handle the extra, because you guys,
I mean, it's been there 120 years before Chadbourne was paved, like the engineers.
no,
that
no,
built
Chad,
Chadbourne
you're dumping it
accounted
into
for it, right?
Chadbourne,
Right,
right?
That's where it drains now.
Right.
That's where it's supposed to.
You're gonna increase,
Yeah.
you're gonna increase
The flow.
the load into Chadbourne by, what do you have on it? What's your, is that your design storm, 10.4 cubic feet per
Yeah,
second?
this is what the district flow, yeah.
So I really don't know the answer to that because the building's been there 120 years.
No, no,
so
I
it's
don't
like-
care about the bill, my question is, did you analyze the downstream? Did you go beyond dumping it into Chadbourne? So you're
No,
assuming,
no.
so you're assuming Chadbourne's an infinite large sink?
Yeah, yeah. 'cause
Yeah.
Yeah.
we
Well,
were-
because it would have been designed to handle the runoff whenever,
No.
like at some point.
No, because you're modifying what's there.
Yeah.
So they're like, oh, well, we have all these warehouses here, but we're gonna build this street with rain gutters and not account for anybody else running their water into them.
I'm pretty sure that's probably accurate, but I don't know.
I wouldn't think so.
Your equation, your I, your intensity and your area is wrong. Area is supposed to be an acreage, and your intensity, 0.816, is not an appropriate in inches per hour. You know, if you're talking a 100-year event, you should be looking at 8 inches per hour, 7
So-
inches per hour for that
So
small of a
I
range.
did not include all the calculations here, but this should be correct, because like we did earlier, we did use acreage here. I didn't just write it there, but,
So that-
but the calculation should be
We
correct.
have your table.
So,
I didn't convert all the units here, that's what I'm saying.
okay, so that's not Q equals CIA, so 0.95 is your C, I should be your 0.816, but that's definitely not your intensity there. And your area is in square feet where it should be in acres, so
In
that,
acre, yeah.
those numbers are not how you got 10.4.
Yeah.
Yeah,
Well, that's confusing.
yeah, that needs to be
So
correct.
this, but the intensity was used based off of, the roof and paved area. This number you get from some
The
tables.
intensity doesn't come from the roof, the intensity comes from your design, right? Design storm, what's the intensity for the design storm?
This for 100 years was that number actually. Let me see if I can bring it up.
Because when you were calculating your
Yeah, it's
intensity,
right here.
you called,
It's on the next one, I think.
you talked about you had a
Yeah.
6.3 minute time of concentration.
Yeah.
Then you said use a 30-minute to determine the Q, and then your hydroflow numbers showed a 14-minute time of concentration. So you were all over the place on your time of concentration numbers.
Hold on. Hold on. So repeat your question again, please.
So at first, you talked about having a 6.3 minute time of concentration you
Right
calculated.
here, okay.
And then you said you used a 30 minutes to determine your Qs.
30 minutes?
When you were calculating your Q, or your intensities, you said you used 30 minutes, I believe, maybe to
No,
calculate.
this is what we use for 1 hour.
So you used so for the rational method, you're supposed to use your time of duration, right? Not your time, not a 60-minute rain event drives down your intensity. If you're looking for a peak number, you need to look at the short duration, the high intensity, short duration event, not a 60 minutes. So
Right, I agree with that, with you, but these are the numbers you input into hydroflow.
Yeah, the question is, why
Express.
did you put those in instead of the 15-minute one? It's, it's 7 point, which, by the way, the client just told you that's when it backed up, because when they got 3 inches of rain in 2 hours or something like that, not when they got, right? I think that's, am I repeating the question correctly?
I think, well, now go, when you calculate your graphs you had shown, that calculated your peak Q, your hydrograph numbers, I think it was after that, keep that one.
Yeah.
You show a 14-minute time there. So,
Right here,
Yeah.
but the peak flow is at 7.
Yeah. Oh, you said that was the time of concentration, but that was incorrect. That is the time to peak. So
Oh, right here I said this is time of concentration?
you said that it was the time of concentration, but it's actually the time to peak.
Yeah.
So I think you did it right, but I think you overshare a lot of different numbers that go into the model,
Mhm.
and that's confusing the audience.
Okay,
Because a lot of these things are aromatic, they put different, they put the constants for the IDF equation. The model can generate intensities for different durations, but it only picks the one that is for the time of concentration, which is the rain event.
Yeah, this points out to me, you know, a significant issue, which I wrote down a bunch of places, like you guys said you did an environmental impact statement. I don't believe you did an environmental impact statement. I believe that you addressed a lot of the environmental issues, and you probably did what you were asked to do, but what you did was not an environmental impact statement. Because an environmental impact statement costs tens of thousands of dollars, it's a whole lot more than you did, and the point is, and then, you talked about the water dissolving into the ground. We're mixing up time of concentration with time to peak. And so this is about language and communications, right? There's a lot of times in here you guys are using inaccurate language. A bunch of the confusion that the professionals are having here have to do with that. And so that's really important to understand. And then some of it's the present, like where you presented the equation, well, that's not really, I guess you're trying to show the calculation, but that's not really the calculation you did, that's really confusing, right? So I think that's a lot of the confusion comes to do with inaccurate language, which like engineers should be able to use exact language when they need to. So I guess that's my main observation from this, because it sounds like a lot of this is not necessarily done wrong, but it's presented in a way where we don't understand what you're doing. And so just so I understand, so the final design is a parking lot with a curb drainage that goes out on the Chadbourne, right? The curb drainage near the railroad, and it just dumps straight on the Chadbourne. Where was the detention pond gonna, can you go back to that that watershed picture that we were looking at? You showed a picture of the detention pond, but I never figured out exactly where you were putting it. The detention basin. I mean, I can't get from that picture to, don't show me that one, go to the site.
It's like,
The one that has the drainage, the catchment basins on it, because I can't. One more. Okay, where are you proposing the detention basin be placed?
It'd be right here. So right here is the existing railroad. There was the previous railroad right here, and it would be right
So it's gonna be long and skinny in this direction, or?
in this direction.
Okay, so just like behind,
It'd be adjacent to the
basically a
parking lot.
long skinny detention basin behind where you put the parking lot?
And the railroad.
Right. And you decided not to do that because, is there anything wrong with that? Is it taking up space is it taking up space from your parking lot or something? I don't understand why you would
The
do.
railroad embankment, they were trying to stop construction over there.
And the easement on the railroad, which we weren't able to
Okay.
find a good
All right.
answer for.
Okay, that makes sense.
Alright, with that, I always make a promise to my team that I'll cut off questions. It's 2 o'clock, I'm cutting off questions.
Will you guys-
Would the client like to state anything else you wish to express to the team or talk?
We absolutely, certainly appreciate the attention that you've given to this. Yeah, I can't say thank you enough for that end of it. As a partial hydraulic student myself, yeah, I come across with some more questions than answers. But I see where you're going, and overall, the presentation, if you would take a hint from a person that has given a lot of presentations and been through, take that laser pointer and throw it in the damn trash. It does not help. It is a distraction, and it's, that, no laser pointers. Not unless you got a really big one or something like that. That little dot going around, I wanna be a cat in it. The amount of time and effort that you put into it is impressive. And, we appreciate being the recipients of this knowledge. And it helps us, going forward. You say you're gonna give us a report that breaks everything down. Oh, you have it? And great. So anyway, thank you very much.
I just want to make one comment to the gentleman who worked with us and have come into our building and was most professional, all of you. I enjoyed being the recipient, number one, but working with each and every one of you. Y'all were both all very, very, very professional, very, pleasant to work with and be there, and was interested in our mission and what we do and why we do it, and what it meant to us to be able to be the recipients of this and to help us figure out some of the answers that we didn't have. And so, again, thank you all very much. It was a pleasure to work with each of y'all, and much, 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 we wish you all much happiness and prosperity in y'all's careers and moving forward in y'all's future. And thank you all very much.
If you have more questions for the team, you're welcome to come up and greet them and talk to them and ask them more things, or just say hi. Take pictures with them, whatever the case might be. But that'll conclude our presentation. So thank y'all for coming. Thank you.
We gotta go talk to Miguel about it.
Thank you so much for coming out.
Good question.
Thank you so much.
He's kind of sitting really still.
Thank you.
Are you taking these?
Nice meeting you. Did you fill it out?
Right.
As we go, if there's
Yeah, good.
Thank you. 2 weeks left.
It feels like